Hello everyone. This is a part of lecture series on stereochemistry from Organic Chemistry section B of your syllabus. In this lecture, we will learn about the different conformations of cyclohexane molecule. Conformations are the structures of a molecule having different arrangements of atoms in space, resulting due to allowed rotation about carbon-carbon single bond. In our previous classes, we have already studied about the different conformations of ethane and butane. The molecular formula of cyclohexane is C6H12, and this is the basic structure of this molecule. Sometimes it is also written as a regular hexagon. But this is not the true structure of cyclohexane. This is because if cyclohexane were a regular hexagon, it would be planar with a bond angle of 120 degrees. But in reality, cyclohexane is a non-planar molecule in which each carbon atom is sp3 hybridized and the tetrahedral bond angle is 109.5 degrees. This will be more clear with this ball and stick model. The black balls in this model represents the carbon atoms, while the white balls are the hydrogen atoms. Each carbon atom in a cyclohexane molecule is attached to two hydrogen atoms. And the ring backbone consists of 6 carbon atoms with carbon-carbon single bonds about which rotation is possible. And this rotation leads to conformations. When we view this molecule from the top, the carbon ring appears to be planar. That is, they seem to be lying on a plane. But when we focus on the side view of this molecule, in its most stable form at room temperature, we find that two of the carbon atoms are not lying on the plane. Hence, cyclohexane is a non-planar molecule, as we can see from this ball and stick model. We will see the reason shortly. In cyclohexane molecule, there are two types of hydrogen atoms. One is called the axial hydrogen, the other is called equatorial hydrogen. Equatorial hydrogens are coplanar to the carbon ring. In these ball and stick models, you can see the green balls represent the axial hydrogen while the white balls represent the equatorial hydrogen. By coplanarity, we mean that if this is the plane of the 6 carbon atom ring of cyclohexane and these are the equatorial hydrogens, you can see that the planes are same. So all those hydrogens which are lying coplanar to this carbon ring, that is these white hydrogens, are referred to as the equatorial hydrogen. And these bonds are the equatorial bonds. Whereas the axial hydrogens, they lie in a plane which is perpendicular to the plane of the carbon atom. So all these axial hydrogens lie on a plane which is perpendicular to this plane of carbon atoms. Each carbon atom in a cyclohexane molecule is bonded to one axial and one equatorial, as is clearly shown in this ball and stick model. Thus, one molecule of cyclohexane has 6 axial hydrogens and 6 equatorial hydrogens. When we rotate the carbon-carbon single bond of cyclohexane, there is a change in spatial arrangement of atoms, and there is also a deviation from the preferred tetrahedral bond angle of 109.5 degrees. This develops a strain in the molecule And to minimize this strain, the molecule attains a certain structure called conformation. We will now discuss the three types of strain commonly observed in cyclohexane. First is the angle strain, second is the torsional strain, and third is the steric strain. This in front of you is the cyclohexane molecule with all hydrogen atoms removed for convenience. We will focus only on the carbon backbone of the cyclohexane molecule to understand what are the different conformations, that is, the possible structural arrangements which are generated by rotation of the molecule about these carbon-carbon single bonds. Before we move on to the conformational analysis, we must first of all remember that these carbon atoms of cyclohexane are sp3 hybridized, and so the most preferred orientation of these carbon atom is tetrahedral arrangement. Hence the preferred bond angle is 109.7 degree. Any deviation from this bond angle induces strain in the molecule and increases the energy of the system, thereby making it unstable. This kind of strain that results in the molecule due to deviation of the normal bond angle is called angle strain. Another type of strain which develops due to rotation about the carbon-carbon single bond is called the torsional strain. As we have discussed the staggered and eclipsed conformations of ethane and butane previously, wherein we had understood what staggered and eclipsed conformations are. In this particular conformation of cyclohexane, if you can see this carbon and this carbon, they are in eclipsed conformation. Similar is the case with these two carbon atoms. Lying on the same plane and viewing from this angle clearly shows that they are eclipsing each other. Whenever these kind of situation arises, it induces a torsional strain in the molecule. Suppose if I rotate these two carbon-carbon single bonds, rotating these bonds further up brings this carbon in plane with the four other carbon atoms. This rotation has caused 5 carbon atoms to be in eclipsed position to each other. Such eclipsing of carbon atoms induces strain in the molecule, and this type of strain is called as a torsional strain. This also makes the molecule unstable by increasing its energy. Another kind of strain that is often seen in cyclic molecules like cyclohexane is the steric strain. As you can see in this particular structural arrangement, these two hydrogen atoms are far apart from each other. But if we continue to rotate these carbon-carbon single bonds, these hydrogen atoms come close to one another and start interacting. And we know that atoms are nothing but electron clouds. Probability distribution of electrons in a three-dimensional region of space. So while performing this rotation and bringing, the two hydrogen atoms start interacting with each other. Since these two are negatively charged electron clouds, this interaction will cause a great amount of repulsion between the electronic clouds of the two hydrogen atoms. This induces strain in the molecule and increases the energy of the system. This kind of interaction is called steric strain. The strain that arises due to this kind of interaction between the electronic clouds of the closely situated atoms is called steric strain. So this particular conformation of cyclohexane, which is the boat conformation, is highly unstable because of this kind of interaction between the two flagpole hydrogens. Hence, we have come to understand that there are three kinds of strain which are normally observed in a cyclohexane molecule during conformational analysis. First is the angle strain, second is the torsional strain, and third is the steric strain. Let us now proceed further to understand how the conformational analysis is performed on cyclohexane. Cyclohexane, as we have discussed earlier, exists in the most preferred orientation, which is called the chair conformation. As you can see here, this is the most preferred orientation of a cyclohexane molecule. At room temperature, about 99.99% of cyclohexane molecules exist in this conformation. See, the molecule looks like a chair, hence the name chair form. This is the first and the most stable conformation of cyclohexane. Now, starting from this point, we will keep these two bonds fixed and we will rotate the molecule about these two carbon-carbon single bonds to generate a series of conformations. Keeping this part fixed, we will bring this carbon atom slightly up by rotation about these two carbon-carbon single bonds. The structural arrangement that you can see now on screen is called the half chair conformation. In this half chair conformation, 5 carbon atoms, 1, 2, 3, 4 and 5. These 5 carbon atoms lie on the same plane. This is an eclipsed conformation and has a high angle strain, high torsional strain, because of which this conformation has the highest energy and it is most unstable. Continuing with our rotational operation further, we will rotate these carbon bonds on the right hand side further up, but not fully up, to generate a conformation like this, which can be viewed from this particular orientation. This is neither chair form nor a complete boat form. This is called the twist boat form. It has a lower energy than the half chair form, that was the previous conformation, and higher energy than the first conformation and the most stable one, that is the chair conformation. Rotating these bonds further up to the maximum possibility, we get the full boat conformation. As you can see here, we get a full boat shape. This is called the boat conformation. The boat conformation is more stable than the half chair conformation, but less stable than the chair conformation. It is also less stable than the twist boat conformation because, as I have shown you earlier, there are two flagpole hydrogens on this conformation which interact with each other, making the system highly unstable due to torsional strain. Now we'll continue our rotational operation on this side. As we are moving in a clockwise direction, that is, we started from the chair conformation, started rotating the bonds, carbon-carbon single bonds, up to this maximum point to get this boat conformation. Starting from chair conformation, we got the half chair conformation, followed by the twist boat conformation, and now this is the boat conformation. As we continue our rotation process in this direction to complete a full cycle, we will get another set of twist boat, half chair and a chair conformation. Let us try to see how this can be obtained. Now we'll keep this part of the molecule fixed and we will rotate these carbon-carbon single bonds to bring the molecule to this position. This is, as you can see, you can view it from this point. This is the twist boat conformation. This is the twist boat conformation. It is more stable than the previous conformation, that is the boat conformation. Further rotating the molecule, the carbon-carbon bonds down, we get this orientation, this kind of structural arrangement. This is again the half chair conformation. As you can see, previously we have seen this conformation in our first rotation while we are moving up this side. This is again a half chair conformation with 5 carbon atoms on plane and the 6th one non-planar. Continuing this rotation further down, we get back the chair conformation. This is where we stop doing the conformational analysis, the rotational operation. So we actually started from this chair conformation and we ended up with this chair conformation. These two forms of chair conformations are mirror images of each other. So while performing the rotation operation starting from this chair conformation like this, we went on to get the half chair conformation with increase in energy of the system as the strain increases. Then further moving up we got the twist boat conformation. Then further moving up we got the boat conformation. Continuing the rotational operation in this clockwise direction here, in the anti-clockwise direction here, we got the twist boat conformation followed by the half chair conformation, and finally we got a chair conformation which is the exact mirror image of the first chair conformation. Now there is no difference between the first and the last chair conformation, both have equal energies. The same goes with the two half chair conformations, they have same energies, and the same applies to the twist boat conformations, they have same energies. But altogether, performing this rotational operation, that is conformational analysis of cyclohexane, we got 4 conformations of cyclohexane. First was the chair conformation, which is the most stable and the stable conformation with lowest energy, followed by the twist boat conformation, which comes next to chair conformation in terms of energy, followed by the boat conformation, and lastly the half chair conformation. So the chair conformation has the lowest energy, hence is most stable, followed by the twist boat conformation, which has next lower energy, followed by the boat conformation, and the next is followed up by the half chair conformation, which has the highest energy. This is the energy profile of the different conformations of cyclohexane. Now if we see the energy profile diagram of cyclohexane, we will find that the two conformations lie on the energy minima of the diagram, that is the chair conformation and the twist boat conformation. These two conformations are called conformational isomers of cyclohexane, or in short they are known as conformers. The remaining two are regarded as conformations, but they are not conformers. So far, the conformational analysis of cyclohexane that we studied by rotating the carbon-carbon single bonds can be summarized as follows. Rotation of carbon-carbon single bond in the chair form gives rise to the half chair conformation, which then gives the twist boat conformation. Rotation of the twist boat conformation gives the boat conformation. Thereafter, rotation of carbon-carbon single bond in the boat form gives the twist boat form. This is followed up by the half chair form, and lastly by the chair form. As you can see, we start from the chair form and we end up in the chair form. These two chair forms are the mirror images of each other, but there is no difference in their energy level. Similarly, the two half chair conformations are mirror images of each other, and the twist boat conformations are also mirror images of each other. There is also no difference in energy levels of the two half chair conformation and the two twist boat conformation. The rotational energy profile of the different conformations of cyclohexane is depicted in this diagram. As you can see, as we start rotating the carbon-carbon single bond of the chair conformation, energy of the molecule starts increasing till it attains a maximum height where we get the half chair conformation. As we have already discussed, the half chair has the highest energy and hence is the least stable of all conformations. Rotation of carbon-carbon single bond in half chair conformation leads to decrease in energy of the molecule up to a lowest of this level where we get the twist boat conformation. As the rotation operation is performed on the twist boat conformation, the energy of the molecule rises further, attains a certain height which is lower than the height of the half chair conformation. Here we get the boat conformation. Clearly, the energy of the boat conformation is higher than the energy of the twist boat conformation, so it is less stable, but its energy is lower than the half chair conformation. Hence, it is more stable than the half chair conformation. As the rotation is continued in the boat conformation, the energy of the molecule further decreases to attain a minima. This minima is same as the minima we had obtained earlier. So this corresponds to another twist boat form. As rotation is continued in the twist boat conformation, the energy of the molecule increases further, attains a maximum height similar to that attained in the first half chair conformation. So we get another half chair conformation here, and thereafter rotation of carbon-carbon single bond performed on the half chair conformation gives us another chair conformation, which is the mirror image of the first chair conformation from where we had started the rotational operation. This potential energy diagram clearly shows the energy changes that occurs in the cyclohexane molecule when rotation is performed about the carbon-carbon single bonds. The four conformations of cyclohexane we have discussed so far can be summarized as the chair form, the half chair form, the boat form, and the twist boat form. Now, these are the corresponding Fisher projections of the three-dimensional ball and stick model. The ball and stick model is just for understanding purpose. When we are going to write the structure in our notebook, we have to write this structure. For the chair form, this one for the half chair form, this for the boat form, and this one for the twist boat form. I recommend you pause the video and practice drawing these structures in your notebooks. Practice them as much as possible until you become thorough. Now we will learn how to write the Newman projection formula for the boat form and the chair form. The boat form, as you see, is an eclipsed conformation. Here, the two carbon atoms here are in eclipsed position. Here also, the two carbon atoms are in eclipsed position. In between, there are two carbon atoms hidden behind this white hydrogen, which are also in the eclipsed positions. So while writing the Newman projection formula, in such a case, we will write a circle for these eclipsed carbons. Similarly, in the chair form, which is the staggered form of cyclohexane, you can see there are two carbon atoms here, hidden one behind the other. So there is one eclipsed position, there is another eclipsed position. In between, these two carbon atoms are not eclipsed but in staggered form. So while writing the Newman projection for chair form, we will put a circle for these eclipsed carbons and a circle for these eclipsed carbons. Let us see how this can be done. Writing the Newman projection for the boat form, you see the two circles are depicting the two eclipsed carbons here. This one in between shows the first carbon atom here. The one just drawn here shows the one which is eclipsed behind this carbon atom. The remaining bonds show the bondage with the hydrogen atoms. Thereafter, in the chair form, the two circles depict the two eclipsed carbons. This point is for one of the staggered carbons. This point shows this another staggered carbon, while the remaining lines show bonds with hydrogen atom. I again recommend you to pause this video and practice writing the Newman projection formula for the boat and the chair forms as many times as possible. हमने अभी तक इस वीडियो में साइक्लोहेक्सेन के डिफरेंट कॉन्फॉर्मेशंस के बारे में जाना और हमने ये भी देखा कि इस मॉलिक्यूल में दो तरह के हाइड्रोजन एटम्स होते हैं. एक एक्शियल हाइड्रोजन एटम जिसको हमने इस मॉलिक्यूल में ग्रीन कलर के बॉल्स से शो किया है और दूसरा है इक्वेटोरियल हाइड्रोजन एटम्स जिसको हमने यहाँ पे वाइट कलर्ड बॉल से शो किया है. अब हम एक ऐसे प्रोसेस के बारे में जानेंगे जिसमें इन इक्वेटोरियल हाइड्रोजन एटम्स को एक्शियल में इंटर कन्वर्ट किया जा सकता है. इस प्रोसेस को हम कहते हैं चेयर फ्लिप और रिंग फ्लिप. जैसा कि आप देख रहे हैं इस साइक्लोहेक्सेन मॉलिक्यूल में ये दो तरह के हाइड्रोजन एटम्स, जो हाइड्रोजन एटम साइक्लोहेक्सेन रिंग के प्लेन के साथ मैच करते हुए प्लेन में है, इन हाइड्रोजन एटम्स को हम इक्वेटोरियल हाइड्रोजन एटम्स कहते हैं. और जो हाइड्रोजन इस प्लेन के परपेंडिकुलर है, ये ग्रीन वाले हाइड्रोजन एटम्स, इनको हम एक्शियल हाइड्रोजन एटम्स कहते हैं. ये कॉन्फॉर्मेशन जो आपको अभी स्क्रीन पे दिख रहा है, ये साइक्लोहेक्सेन का सबसे स्टेबल अरेंजमेंट है, दैट इज चेयर कॉन्फॉर्मेशन. इस चेयर कॉन्फॉर्मेशन में अभी आप देख रहे हैं कि हर एक कार्बन एटम के साथ एक एक्शियल हाइड्रोजन है और एक इक्वेटोरियल हाइड्रोजन है. सभी कार्बन में एक इक्वेटोरियल हाइड्रोजन है और दूसरा एक्शियल हाइड्रोजन है. And the same goes with all carbon atoms. अब हम क्या करेंगे, इस रिंग को फ्लिप करेंगे. फ्लिप करने का मतलब है कि इस चेयर कॉन्फॉर्मेशन को हम एक दूसरे चेयर कॉन्फॉर्मेशन में कन्वर्ट करेंगे और ऐसा करने से जितने भी एक्शियल हाइड्रोजन अभी आपको एक्शियल दिख रहे हैं वो फ्लिपिंग के बाद इक्वेटोरियल बन जाएंगे और जो इक्वेटोरियल है वो एक्शियल बन जाएंगे. लेट अस सी हाउ दिस कैन बी डन. इस फ्लिपिंग प्रोसेस के लिए हम इस कार्बन एटम को और इस कार्बन एटम को एक साथ रोटेट करेंगे, यानी कि फ्लिप करेंगे. इसको हम ऊपर उठाएंगे और इसको हम नीचे लाएंगे. इसको आप नीचे ट्विस्ट करेंगे और इसको आप ऊपर, इसको ऊपर और इसको नीचे करने से we will get this kind of conformation, which is again a chair conformation. This is again a chair conformation. But see the difference what has happened. All those bonds which were earlier axial have now become equatorial. आप इस व्यू से देखें तो आपको समझ में आएगा। पहले इस प्लेन पर जितने भी हाइड्रोजन एटम्स थे वो वाइट कलर्ड के थे, यानी अभी हमें जो दिख रहा है स्क्रीन पे वो ग्रीन कलर के हाइड्रोजन एटम्स हैं। यानी इस तरह के प्रोसेस से हमने क्या किया, सारे एक्सियल हाइड्रोजन एटम्स को इक्वेटोरियल पोजीशन पे कन्वर्ट कर दिया, और जितने भी इक्वेटोरियल हाइड्रोजन एटम्स थे अभी आपको दिख रहे होंगे, वाइट कलर्ड के जो हाइड्रोजन एटम्स थे जिनको हमने पहले इक्वेटोरियल लेबल किया था, अभी वो एक्सियल पोजीशन पे हैं। सो इस प्रोसेस को हम कहते हैं रिंग फ्लिप या चेयर फ्लिप। ऐसा करने से साइक्लोहेक्सेन का एक चेयर कॉन्फर्मेशन दूसरे चेयर कॉन्फर्मेशन में कन्वर्ट होता है, और साथ ही साथ जितने भी एक्सियल बॉन्ड्स हैं वो इक्वेटोरियल बन जाते हैं और इक्वेटोरियल बॉन्ड्स एक्सियल बन जाते हैं।